Good morning, everyone. It's really my pleasure and a particular pleasure to introduce our seminar speaker today, Dr. Yida Zhang from the University of Colorado at Boulder, where he's an assistant professor. And I'm really proud to say that Yida is really one of our own. He comes from Northwestern. He graduated with his doctoral degree here in this very department. Prior to that, his bachelor was awarded in China at Zhang University. And he also has a master's from Louisiana State University. Yida's interests in research are wide-ranging, very broad, very deep on theory and mechanics. His interests span from pore mechanics to granular mechanics to crushing processes and more. And today he will show some of his exciting work on the hidden role of surface forces in the mechanical behavior of fluid-saturated porous materials. Thank you so much for coming. Look forward to your talk.
Thanks, Giuseppe, for the excellent, nice, introduction. So it's really my pleasure to be able to give a talk here, and I think indeed I delivered my PhD defense exactly in this room about 6 years ago. So time flies, and it's really an honor to have share my research to my former professors and colleagues and friends and even former students. So anyway, my topic is on hidden role of surface forces, and whatever the topic. And so let's get started. And essentially, first of all, porous material is ubiquitous in nature and engineering. Humans extract the resources and energies from the pore space of underground reservoir rocks. We engineer novel nanoporous materials to create large pore space, high specific surface area to be able to capture gas and store gas and for catalysis purposes. Biomaterials such as wood and even our tissue in our body are porous materials because they maintain their structural integrity, meanwhile allow fluid to transport in and out. So ways to describe the mechanical behavior of this type of materials usually is pore mechanics. Essentially, we view a porous material as a superposition of a solid phase and a fluid phase in the same spot. The total stress is shared by both pore skeleton and the pore fluid. The portion shared by the skeleton is characterized by the effective stress. Here, sigma is total stress, P is pore pressure, C is the Biot coefficient between 0 and 1. If the pore become partially saturated, then we can model it by changing some equivalent definition of pore pressure as a function of suction or saturation to capture the additional effect of the tension induced by the formation of water menisci. From that, we can capture the volume change of porous media during drying and wetting. But what captured my interest in this line of research is really this series of experiments on natural coals. Coals are porous media with multiple levels of porosity. If you place a coal specimen in a vacuum chamber and pressurize the chamber with gas, then plug this condition in the effective stress equation, we predict the overall negative force, which means contractive stress, and then this is pore-elastic prediction. But the experiment shows entirely opposite direction. You observe swelling. And that swelling strain usually range between 2 to 3%. Is a function of the gas type. It's also a function of the coal type. If you look at the absorption isotherm of this material, you can see that it looks similar to the strain isotherm with different gases. So it is hypothesized that this is an absorption-induced deformation. So what is missing in the classical framework to not allow us to capture this? One of the hypotheses is that we are missing the surface tension. This is also called Benham effect or Benham theory. Basically, absorption process will interact with the surface tension to cause some change of the skeleton stress, and that will induce this effect. Before we go into this topic, we can define surface tension in different ways, but here let's look at the thermodynamic definition. Basically, if you place a fluid in a absorptive fluid, the fluid density will vary continuously when it's near the solid, and because of the attraction between solid and fluid molecules. Describing that system is difficult because it's varying everywhere. So Gibbs comes in and say, let's lump all this additional mass into a zero thickness interface and call that a surface excess phase. Now your system is solid, fluid in the interface. Perturb that with respect to surface area change gives you the thermodynamic conjugated force, that's the surface tension. For derivation, you can derive the Gibbs isotherm, tells you how surface tension varies with respect to the amount of absorption. That tells, that can be further linked with the swelling. However, there are many missing parts. For example, pop-up scaling, because surface tension is a local pore wall property, while what we're interested in is a global pore mechanics response. How about effective stress? And how does that lead us to quantitatively predict soft strength? So that's motivated me to do this on this work in 2018, where I want to consider the most general scenario as possible. So we set everything up in this Cartesian coordinate. We considered finite deformation and from reference current configuration. Each material point can have a solid phase and fluid phase. Each of them can follow their own kinematics. Fluid phase, I will consider the most general case where it can be k different species, so a fluid mixture. What's the more, I would say, the innovation in this work is to add this additional surface phase in the same point. So it's a three-phase mixture, and it contains k species as well, and it's exchange mass with fluid through sorption and desorption. So once this is set up, we can follow the standard formalism of thermodynamics of the theory of mixtures to list the mass, momentum, energy balance of each phase. Combine them with second law, give us the so-called Clausius-Duhem inequality. What this says is essentially, I forgot about the name. It says the dissipation, energy dissipation in the whole system while it's moving or having some changes inside must be greater or equal to zero. And each of this is a different physical process. You can further state a stronger condition saying each of this must be non-negative. That will lead you to derive the Darcy's law, Fick's law, Fourier's law, and for hydraulic, thermal, and the chemical diffusion processes. Then the mechanical material dissipation characterizes the inelastic process. But here, let's focus on the solid dissipation. If I say I want to look at the reversible process, then you set the dissipation equal to zero. This gives you the free energy balance of a surface, active or solid. In addition to the traditional terms, these are derived from Cauchy, we have this additional term from surface. That's the consequence of considering surface in the system. What it says is that you can store energy in your porous media by the following patterns. Isotropic compress it, devitorically load it, deform it, or pressurize the pore fluid to change the pore space, or expand the surface area by working against surface tension. And a closer inspection of this picture tells us that porosity and surface area should not be independent of each other, because you can change one without changing the other. You can also explore this dissipation by considering an irreversible process and say that greater than zero. Then we can write this in this format, that the dissipation can coming from plasticity, damage, fracture, green breakage, and so on. So at the end of this talk, near the end of this talk, we're going to explore this, but here we will mainly focus on the elastic properties. For elastic solid, then let's explore that. Plug in this geometrical relation, get the constant equation in this format. Everything is similar to the classical Cauchy's derivation, except pore fluid pressure now is modified by a PA term from the surface, and that PA we can call it sorption stress, which is a multiplication between surface tension and the geometrical factor that characterizing the tortuosity of the pore network. You can see that the left-hand side is a macroscopic stress because it enters the constitutive law. On the right-hand side, it's the local pore wall property surface tension. So through that, we achieve the upscaling. If you further say the isotropic for elasticity, then effective stress looks like this with this additional term. What this equation says is that you bring a pore solid in zero total stress, inject zero pore pressure, you're still going to have the material subject to a pre-stressed tensile or compressive stress. So this is negative. So essentially, it has been already pre-stressed in vacuum. So whenever you do absorption where surface tension reduces, that relaxes the skeleton. So that's manifested as a swelling. So essentially, this is the mathematical version of the Benham theory. Remember, up to this point, there is no constitutive level hypothesis. So everything is derived from the first principles, everything from energy balance. So that will benefit us for the generality of the framework. And later on, we will show. But right now, let's specify these constitutive components to build a model out of it. You can choose a Helmholtz energy potential in this quadratic format. Let's give you the linear isotropic one. You supply in this simplest absorption model, the Langmuir's equation. Plug in the Gibbs isotherm, gives you the surface tension reduction as a function of gas pressure. Then you can consider a microstructure. Here we consider a thick wall hollow sphere that leads you the relation between surface tension and the velocity. All of the parameters shown in this slide have clear physical meanings and it can be calibrated from routine lab tests. So no phenomenological injected here. And let's see the model performance. Here we compare it with the data from holes and spheres on this Rizes code. The open circle are data from carbon dioxide injection. You can see swelling about 2% on strain. And they also did the same test with helium gas. That helium is an inert gas, so it doesn't interact with pore wall. So whatever you see here is a pure pore elastic compaction component. From there, you can calibrate the Young's modulus of your model. And then the difference between these two give you the pure absorption-induced strain. You can see the model successfully captured all of these. But if we want to look at the individual strain component along different directions, their data shows different values because of the intrinsic bedding plan of the code. Well, our models only give you one curve because it's isotropic. Then here is the benefit, because the existence of absorption stress does not depend on constitutive assumptions. It's from the energy balance from the first principle. So essentially, you can swap in and out different Lego blocks to make your model more material specific. So here we can make a transverse isotropic elasticity model, and immediately we can improve the model by having the Z direction strain different from the X and Y direction, right? Of course, you can argue X and Y are also different, then you can plug in an orthotropic elasticity model. That's no problem. But we want to try something else. Remember, the model is built with K species. So what about 2 species, right? At least let's test with a methane carbon dioxide injection in coal. Then we keep the same pore elasticity component, but change the absorption model to a extended Langmuir equation, capturing the mixed gas absorption. Then immediately we can predict the absorption-induced strain in a different percentage of carbon dioxide injection, and the data is from day. Also, we can pre-saturate the chamber with methane and display it by carbon dioxide, and this is a predicted volumetric strain, all captured with one set of parameters. So then you can be very creative within this framework. For example, we are looking at the pine cone. You know, these pine cones we see every day. When they are up in the tree, they are supplied by water from the stems, so they are closed. You know, once they fall down on the ground, they dry up, and their scale will open up to release the seeds. So it's a seed dispersion mechanism for pine tree, adopted from the history of evolution. So you can see this deformation is definitely huge, large strain. Mechanical engineers and material scientists trying to do replica of this process to invent or inspire new actual passively actuated materials for gas sensors or actuations. So to model this process, we need to have a finite strain model. So we choose the Netjar's model, where the first term captures a neo-Hookean elasticity, second term gives you a nonlinear porosity law, and then let's run the same test. You can see I focus on the elastic compaction component. The linear theory will give you a monotonically linear decreasing trend. And by the way, here is the vertical axis is J, the Jacobian, defined as the current volume over the reference volume. You can imagine that once it's pressurized larger, it's going to cross zero and become negative. which is unrealistic because the volume of something is never negative. But the finite string version is able to remediate that problem because the swelling string can be 200%, could be very large. Of course, to fully model this process, we need much more than a constitutive law, right? We need to solve the coupled diffusion, finite deformation equations, and we need to put in the right boundary value, boundary conditions, and so on. So that's a future work. That's something we're currently tackling. But at least we can start to solve this we can start to apply the small string version of the model in a boundary value problem setting. And we choose the problem of co-bed methane production. So this is a process where the engineers opens up a hole in the co-bed co-seams, and the co-seams have high pore pressure in situ, but this well will reduce that pore pressure to release the pre-absorbed methane on the co-surface. That produce methane, that's a production of co-bed methane. Co-structure looks like that. Then we opt to set up this very simple two-dimensional plane strain geometry where the gaps are the fracture. They are modeled by continuum elements with non-sorptive models. The flow in the in the fracture is governed by Darcy's law with the cubic law. And the big blocks are co-matrix. The flow is also the same equation, but the permeability is governed by cosine carbon equation. Then we can put it into a triaxial test setup. Everything is brought to equilibrium with the initial in situ state with the high vertical stress, high pore pressure. And then we do a deflection path, meaning keep everything the same, but reduce the pore pressure. As you can see, everything, this is the path along the bottom of the sample. The horizontal strain is zero everywhere, but as the pore pressure starts to reduce, the matrix part starts to have negative strains, meaning shrinkage, right? So absorption swelling, so desorption shrinkage. Since it's in situ condition, so the horizontal strain is fixed in the boundary, then the fracture must open up to compensate for the matrix shrinkage. Indeed, you can see the fracture element has a positive, about 160 positive horizontal strains. And that micro change between co and fracture will be reflected in the apparent permeability of this co. If you stop at each pressure level and run a permeability test, you can see that this is the data from Mirtra. They have in situ point here, and then a reduction of pore pressure gives you the apparent permeability increase of about 15 times. And the green ones are the field data from San Juan Co basin, and it shows similar trend, about 10 times. So our model is able to, with different fracture to co ratio, gives us the end members of this trend. And then you can play with parameters by changing permeability ratio, modulus ratio to create all these different types of permeability evolution law. Rising type, rebounding type means decrease first and then increase, decline type. So all of this has been observed in lab and in the field. Coming back to the sorption deformation problem, have we solved everything? I was pretty happy after that paper published in the JMPS, and then I come across this literature showing the similar test on activated carbon rod. These are different type gases, 1957. You can see their test shows that initially the sorption will induce a small shrinkage regime. And then after that, it's the usual Banham expansion. And that applies for all gases, they see. Then we'll think, okay, maybe that's too early of a test. The precise is not there. But then recently Bowser did another set of tests on synthetic carbon. And you can see initial shrinkage, the low amount of absorption, then later is the expansion. Keep in mind, all of this has nothing to do with the capillary bridge, because the stress pressure level here is about 10 to the minus 3. So at that level, not even the first layer of absorption has been covered yet. So that is not due to capillary condensation. If you look at the pore size distribution, it's fine that this material has a large amount of nano pores in the small, in the sub-nanometer range. So we speculate that it has something to do with that. So this cannot be captured by Manhattan theory alone or the surface tension alone. So we can do a pore scale analysis. These are the meso or micropore we are considering. You can see that for this kind of geometry, sorption on each surface kind of happen in an independent way, right? They develop their own surface regime. In the middle, you get the bulk fluid property shows up. And if you go through the Gibbs treatment, this is the pore total internal energy in the pore. It's the same thing as before. But if you were to consider a micropore, then this interfacial region start to overlap, and the density is higher everywhere than the bulk fluid property. So nowhere in this pore you have the bulk fluid flowing. Everything is relatively structuralized. So to remediate for that, we propose to add this additional correction term on the work input to the system that captures the additional energy you need to supply to change the pore size. And that capture is responsible for the, captures the overlapping effect. Here, pi is a pressure term, A is the pore surface, H is the pore size. And pore volume and area is related with pore size, so you can regroup these terms to the previous one. Once we do that, the micropore is now treated as if it was before, but with the pore pressure updated to the P plus pi. That pi is also called disjoining pressure in a lot of material science literatures. The surface tension is also modified with that pi term. So once that is done, you can see the Gibbs isotherm need to be updated to incorporate pore size change effect. That's not helpful too much, but if you examine its Maxwell relation and integrate, you can get the explicit expression of the disjoining pressure and surface tension from thermodynamics alone. These two are the most important concepts, I would say, in this framework, which I call surface pore mechanics. Essentially, I call them surface force terms, or in simple, surface forces, because for two reasons. First is that they will never show up in your formulation if you neglect the surface in the interface between solid and fluid. Second, they both have deep roots in the intermolecular forces at nanomolecular scale. And they are essentially caused by solid fluid interaction due to the existence of a surface force field near the surface. And that pi captures all this interaction normal to the pore surface, to the pore wall. Gamma captures all this interaction tangential to the pore wall. And they are kind of surrogate to all the rich interactions happening. There are dedicated fields like surface science study these kind of forces. So I would say this is a good bridge, our vehicle to carry all this good stuff into our continuum modeling of porous materials. To further write their expressions, we need to specify the disjoining pressure, the absorption isotherm as function of pore pressure, P, and pore size H. And to hunt for this absorption isotherm is difficult for us, but we come across, after 2 months, we come to this paper by Bronner, Deming, and Teller, or the called BDDT isotherm. Here, the B and T are the same guy as the BET theory. So they use the same stochastic processes to derive the absorption inside a nano-sized slit pore instead of the free surface. And then they come up with this equation as a function of normalized pore size and normalized pressure. If you plot it out, it perfectly describes the intuition that we have is that for small pore sizes, the pore quickly fills and you see a Lamour type of absorption. For large pores, then the walls can keep building up, the layers can keep building up, then you see a BET type of absorption isotherm. And in the middle is smooth transition. So it's perfectly suit our goal, and then we'll plug it in there. Of course, the integration is challenging because this is very highly nonlinear. And of course, you need to then give it to the PhD student, and then he will give you this following result. So you can see the change in surface tension is boring because it's just monotonic decreasing as what shown before. That usually does to the swelling. But the disjoining pressure profile looks more interesting because at small pore sizes and small relative pressure, you see a deep attractive well shows up. That attractive force between two walls will usually bring us shrinkage. So at least for this regime, we have some competition going on between pi and surface tension. Then the question is, who wins? To answer that question, we need to upscale all this force scale analysis to a continuum. You go through theory of mixture and come up with the macroscopic free energy balance with everything consistent with the force scale analysis. Then the absorption stress is now updated with the two terms. This is a mathematical manifestation of the competition we just talked about. If the surface tension term wins, swelling. If the discharging pressure term wins, shrinkage. Then you move on and you can plug in some regular parameters of the swelling contraction phase diagram, as a function of relative pressure and relative pore size. These are too detailed, just roughly, you can see shrinkage regime shows up for small pore size and low relative pressure. Beyond that region, it's swelling. Then we can put it to further quantitative analysis. We use Bowser's data. Right now, the model can only take one pore size in it. So we pinned it on the nano pore size range here. We didn't put it here. And then we run a prediction. You can see the string isotherm is now perfectly captured, including the early shrinkage and also the later expansion. But the absorption isotherm is now far off because it's quickly saturated and flat, as opposite to the experimental data. So we thought it has something to do with the neglection of the larger pores. So then we can generalize the model to consider n different copies of sizes of pores. Here you can see that you need to use the smeared discharging pressure and surface tension in the formulation. Here we use 107 different pore sizes to capture the pore size distribution of the Bowser's data. This is a cumulative one, and the new prediction looks like that. Now the later increased absorption amount is perfectly captured with this, thanks to the inclusion of the meso or macropores. So all of these are good, but one thing that left my impression is that if discharging pressure is so dominating for spaces that is at nano sizes, what about crack tips? Because cracks essentially are two planar surfaces converge at some point at the crack tip. So there must be a region that you have nano sizes, of course. What about the discharging pressure there? If you look at the linear elastic fracture mechanics, they consider remote stress or forces to calculate the stress intensity factor at tip and compare that with a material property called fracture toughness to determine whether fracture is gonna grow or not. If we were to consider this surface force effect, then the picture needs to be updated in this way, where along the crack between the two surfaces, there is a continuous distribution of surface force. Near the tip, it's strongly attractive because that's what predicted from the BDDT theory. And then in the intermediate range, you have some repulsion shows up. And then later on, the separation is too large, so everything is gone. Then if you consider that the effective local stress intensity factor at the tip going to be updated with this format. One is from the surface force, the other one is from the applied stress. And in fact, this is not the first time we come up with this, someone come up with this idea. In fact, as early as 1960s, Barenblatt and Dugdale and so on, they have proposed this cohesive crack model that they consider some finite attractions exist between two already separated fracture surfaces. If we consider that, then the stress field near the tip is updated to this. The local stress is no longer infinite as predicted by linear elastic fracture mechanics. It becomes finite. That means the effective stress intensity factor must be 0. But we would like to highlight, we want to distinguish from the cohesive crack theory set of line of work compared with the surface force inspired fracture mechanics, SFFT. We call it just for temporarily convenience. But the first reason is that cohesive crack model extensively consider this cohesive from its name, from this attractive force. And that can be linear, bilinear, or other relation that's a constitutive law that you just choose one that can match your macroscopic fracture mechanics data. But we want to highlight that the surface force model do not make that assumption. So we take the surface force from the physical the interaction between molecules and surfaces to come up with the surface force. For example, the celebrated DLVO theory considered van der Waals attraction and the electrical double layer repulsion for this surface force computation. If the van der Waals dominates, then indeed attraction shows up. But if electrical double layer repulsion is dominating, then it will surprise the attractive range. And the other difference is that the cohesive crack model, the separation where traction effective is usually at a scale of micrometers, even millimeters. But here the separation is, you can see, several tens of nanometers, so very, very small range. And in the other hand, the benefit of considered surface force is that people have come up with, developed or invented the very precise equipment to measure this surface force directly, including surface force apparatus, atomic force microscope. These are the data compared against the DLVO fit. You can see this is silica surface force in salt solutions with different concentration. And you can see it is strongly affected by the environment, this surface force. And majority, you can see that repulsion dominates in this solution environment. So that highlights the, you can see that this strong environment dependence is where we're going to make some distinguish. And if we want to study a problem that highlight this difference, then if we want to focus on something that depends on the environment, because that's not was incorporated before. Then the prominent problem is the environment enhanced cracking. And this is a high-speed video for a glass cracking, glass that is cracking. You can see that in the instantaneous of the impact, the stress intensity factor is super, super high, far beyond the fracture toughness. Then that you're gonna get a very fast crack propagation from the in-vacuum kinetic equation. But if there's some reactive species present in the environment, then the crack is allowed to propagate at a much lower stress intensity factor, and also at a much, much smaller velocity. This is also called subcritical crack growth. This is a typical shape. Region 1, region 2 is a plateau due to fluid transport, and then at higher intensity, you join the in-vacuum propagation kinetics. In nature, there are many examples for subcritical crack growth. This is the example. These authors studied these arches in Utah national parks. They identified cracks along these arches. Then they run a three-dimensional finite element model to identify the stress distribution in the arches and find the regions where some tensile stress shows up, corresponding to where they can find a crack. Of course, there are many other reasons can cause a crack, but since these are very strong correlations, they suspect this caused by subcritical crack propagation. These tensile stress are much, much smaller than the intrinsic fracture toughness of sandstone, so it must be in the subcritical range. To model this curve, you can use the celebrated Charles law, it's a power law equation, but it can only capture a part of this curve. You put it in the region 1 or region 2, region 3, you can't capture the smooth transition between three regions, and underlying physics is missing. So let us explore this problem in terms of the surface force perspective. We choose to study the problem of crack growth in glass. It's a set of data from Widerhorn on a double cantilever test. This is a relatively dry environment, wet environment, and you can see humidity increase will cause you reduction in the threshold. So to model this problem, we need some key physical ingredients. First, we need something to tell us the crack opening profile and the local effective stress intensity factor. That can come from linear elastic fracture mechanics. Second, we need to resolve the vapor transportation along the crack. It should look like this, the profile, because in the environment, it's always controlled humidity. But at the crack tip, since the crack is keep propagating, so new surface area is constantly produced. And that instantaneous of that moment of production must have zero vapor concentration at the tip. So it should look like that. Then we need a surface force model to take the local relative humidity and the local crack opening to tell us what is the resultant destroying pressure or surface force at that location. It could be attractive, repulsive, or nothing if the opening is too wide. Finally, we need some model to tell us what is the propagation velocity. So here we use this equation as a function of effective stress intensity factor taken from the reactant rate theory. So among all these components, the part that with much more with relatively bigger uncertainty is the vapor transportation. So we consider two modes of transportation along the crack. One is the bulk gas flow, basically viscous flow, and we consider mass balance of fluid in a varying size slit. And then we plug in the bulk gas flow equation, the cubic law. We can get the pressure, the humidity distribution along the crack. You can see as velocity of the crack is higher, the tip region has lower concentration of water vapor. You can also consider the transport in the absorbed layers. That's a surface diffusion mechanism. Similarly, we use surface diffusion equation. Here you can see the overall diffusivity is proportional to the surface coverage. And the similar trend is predicted. Then let's see the model prediction. We couple all these components together. It's a challenging task to solve numerically because it's highly nonlinear and the spatial range is huge. But it took us about half a year to solve it. The students are really good, so we will get the result. And you can see in vacuum, the crack tip indeed give you a smooth closure when the effective stress intensity is nearly zero, as predicted from the cohesive crack theory. But once you apply higher stresses, then it becomes more blunt and the crack is propagating quasi-statically forward. And this is the distribution profile of the surface force. You can see the effective range it acts is about 300 nanometers, so very, very tiny. Here is the prediction result. And at first we just see the data without even the result, without even any data. We're pretty happy because the region 1, region 2, and the joining to region 3 is naturally predicted from a continuous framework. And it's mathematical. There's no assumption about how this should look like or how that should look like in a power law sense. It's naturally predicted. Secondly, we'll plug in the cubic law diffusion 1/12. We see that it overshoots the Plato velocity with the data in the fully humidity environment. So we just change this term compared with surface flow. You can to have all the curves pinned at the Plato velocity to compare their shapes. You can see the different diffusion mechanism will give you a different shape of the subcritical crack growth curve. And that highlights the importance of getting the transport mechanism right. If we vary the humidity, this is what the model predicts. Okay, for both bulk gas flow and surface diffusion, we have only a limited range of change. But the real data from 0 to 100% humidity is much larger change in the Plato velocity gradient. So what is missing? Then we speculated it's because our highly simplified transport model again. In reality, for a gap that has much varying sizes, the transport mechanism could be multiple, right? For example, at larger gaps, the bulk gas flow must be dominating because they are so fast and effective. But at very small gaps, remember there's a term of W squared in there. So that bulk gas flow quickly dies out. Whatever left should be surface diffusion or some other molecular diffusion mechanism. And but we don't have that tool to continuously predict this variation or the transition. So we just opt for this simplistic profile with a straight line behind a certain threshold width. And after that, it's surface diffusion. And then that location of the transition, we make it dependent on the environment humidity, introducing this only ambiguous parameter H in there. But that allows us to do the best fit with the model, with the data. Here is the final result. You can see indeed, the transportation is what controls a lot of the features of the SCG behavior. So you can see our model finally is able to capture region 3 slope, it's power law. You can get the stress reduction with respect to water vapor concentration. You can get the Plato velocity as a function of the humidity as well, governed by gas transportation. And all of this is from mechanistic forward prediction instead of a best instead of like a fit. And I want to highlight this work is a collaborative work with Lawrence Berkeley National Lab. And they're a group that is actively doing experiments to complement with our theory. This is Dr. Seiji Nagakawa, is one of the best rock mechanics experimentists I've ever worked with. So he's basically developing his own double torsion test with that is able to not only load it to cause cracking, but also apply a lateral stress to cause healing. So he can study two processes in one setup. And he opened up the windows to let the light to propagate through the specimen in hope to capture some photoelastic effect. So he can propagate a polarized light. Here it's just very preliminary data. If you look at black and white, you can see indeed the fringe pattern, which highlights the stress concentration is coincide with the optical crack tip, which before nobody confirmed. Maybe is the optical crack tip the real crack tip or not? Is the real location of the stress concentration or not? That's unsure. But anyway, here he pressurized with his finger, then caused crack growth in this glass. And then he released the force on his finger. Then the crack healed immediately in front of his eyes. So it's just retracted. And we are fascinated by this instantaneous healing. And we're trying to see if the framework now can be used for healing. But on the other hand, he machined a lot of these glass discs and put in the polarized light. And you can see the stress concentration cause cracking because these are real glass. These are not the rubber. And you can control the humidity by a water drop here. Again, very preliminary data, but you can load it or hold constant to see crack propagation in time. That's the real STG. And you can upscale this system to a much bigger ones. You can see at the end, these are the cracks caused at the grains boundaries. So that we study this in hope to explain the brittle creep observed in brittle rocks, which is of interest from geophysics, geoscience point of view. Actually, to model this system is the surface pore mechanics framework can easily model this system. If you remember, previously another route is to look at the free energy imbalance. Look at this equation, and then we specify this term. The surface area growth is related with the breakage of the system because breakage causes smaller particles, increase the surface area. And consider dissipation as source of come from plastic strain breakage. You can then establish an elastoplastic model with, here is a teardrop surface in PQ space, and it expands in terms of breakage. And then you can, because the surface tension is there, and surface tension is a function of the environment, then you can model the humidity-dependent variation of the compressibility of these crushable granular systems. Here it is a rock field material, and you can see in dry environment, it's very strong. In wet environment, it's compressed much more. You can also do the creep test, let it creep in dry environment, but once flooding occurred, it triggers a second phase of creep. So all of these environmental effects can easily inject it to your geomaterials models involve the surface effect. And then the first thing I did when I started in Geoboulder is to hire a student to implement the model in a UMAT environment. And we modeled the Shibuya Dam, which is the tallest concrete face rockfill dam in the world at that time. And here is the measured and predicted settlement profile. You can see when it's just constructed, the maximum settlement happened in the middle of the dam, and it's about 2.2 meter. Our simulation shows the similar location and also similar magnitude. And when the load is hold constant, static for the 4 years, there's no seismicity or anything, the sediment grows to 2.45. Our model automatically gives the same amount of creep deformation. What's more is that the model can give you the distribution of the internal breakage inside the dam. You can see after construction, the severe damage is only small, but after 4 years, it grows much bigger. So finally, I want to summarize this talk by this picture. So basically, all the surface forces are rooted in intermolecular interaction and can be studied in molecular dynamics simulation or DFT simulation and so on. And that causes solid fluid interaction, causes absorption, structural ordering of fluid, density variation, anisotropic pressure, and all that. But all of this Luckily, we don't need to worry about them to resolve them spatially because of the thermodynamic analysis give us these two surrogate kind of terms, surface tension and destroying pressure. One parallel to the surface, this one normal to the surface. Consider the surface tension alone allows to capture breakage damage, swelling of micro meso porous media. Considering the competition between surface tension and destroying pressure give us the early shrinkage of micro porous media. Consider destroying pressure along the crack surface allow us to model subcritical crack growth in brittle solids. So finally, I want to thank my PhD student. This is the one that I mentioned several times. Really helped us get a lot of figures. Betty Iskandari Gandhi, right now is a postdoc with me. Thanks Lawrence Berkeley collaborators, Seiji, Han, Ben, and Steve. And I acknowledge my, my sponsors. All right, thank you very much.
Exciting talk, really inspiring results. Let's open it for question. Professor Zhang.
Very interesting talk.
Thank you.
But I would like to point out that many of these problems have been studied for a long time in cements.
Rock dams.
And also in cement physics. Cement.
Okay.
And also in metals, actually. Hydrogen embrittlement is the same thing that is described here.
Oh, okay.
Rise in 1970s, weakens the cracks, absorption, right?
Mm-hmm.
Now, you speak of surface tension, but I think it's important to distinguish between surface tension with a solid and the adsorbed water is always in compression,
right?
Spreading pressure. And if you have a globule surrounded, and if you decrease concentration, of course, pressure goes down, and that causes shrinkage.
Yes.
So that's, of course, disjoining pressure too. That's
yes.
That's also well accepted, I think, in cement disjoining pressure.
Exactly. Yes.
And regarding the isotherm, you speak of BET isotherm. Now, I cannot get it across, but we have a absorption isotherm in nanopores,
yes,
which is different equation and fits much better.
Yes.
When you have nanopores, not just capillary pores, you need to use our isotherm.
I studied that one. And actually, the reason we can find this, we find this BDDT isotherm for a slit pore is because I attended your talk in the EMI.
I see.
And so you basically said, okay, this is the stochastic procedure using BET. Why don't we study this in a kind of tilted slit geometry that give us the Zhang, Said, isotherm. And I said, okay, that's a very good thing. Why don't I take that? But then we figured this paper is probably fit better with this picture where we're studying the slit pore. So we just go for this simpler equation.
But slit pore is okay, right?
In principle, we can use yours as well. So yeah, it's the constrained isotherm, very elegant and very good work. Yes.
It fits better than data for cement, probably also in your case.
Yes, I totally agree. Yeah, very inspiring works from Zhang.
So there was a question by.
Oh yeah.
Yes.
Actually, I have two.
Yes.
Do you consider like a higher order for gamma? Like usually for gamma, it like kind of shrink or like expand the area, right? If it expand the area, like somehow it can allow more.
Absolutely. So basically, that's the string dependent isotherm, and you can capture this. So in that 2018 paper, I have I have a lot of supplementary data here. One of them is this. So we can define surface stretch, surface strain, epsilon A in a logarithmic way. And then you can plug that into your absorption isotherm. You can say that is a dependent on the surface stretch as well. Here, I just put a linear term, 1 plus C in there, but you can make it nonlinear. Once that is incorporated, then this is the predicted result. If this C equal to 0, that means no coupling between deformation and absorption, then you get this result. But if it is function of the strain, then you predict more absorption can happen on your stretched surface, and the shape of the absorption isotherm is also changed from this or to that effect. So you can study that, or you can even make the C negative and so on. So that's definitely important. And in fact, when the surface is stretchable, surface tension concept should be replaced by the surface stress that is proposed by Shuttleworth's equation. Yeah, and yeah, so there are a lot of things to explore along that direction, because the Shuttleworth equation tells you surface stress, but that's again a scalar. In fact, what if you stretch the surface along this direction or this direction? So it really should be a tensor.
Right.
And that line of research is actually much earlier, similarly studied by the Gerten and the Murdoch. They have this surface elasticity theory to capture the tensorial surface stress. But I don't think they have motivated from a thermodynamic point of view. They just say there is a tension along solid surface and it is a tensor. Let's explore what's the consequence. So, but all of this, now I'm seeing they are connected. It's a surface stress universe, I think. Yeah.